Marina Derkash, it's 115. Title, A Robust Brain-Computer Interface for Reliable Cognitive State Classification and Device Control. Thank you.
Okay, good day. I hope you can hear me.
Yes, you fine.
Okay, we can start. Mm, the purpose of this work is to implement a robust and reliable brain-computer interface framework then that enchains real-time cognitive state classification and device control. Um, in the context of increasing demand for innovative human-computer inclusions, the research addresses the internet challenges of EEG signal variability and processing contains. By improving the dependability of BCI, we aim to facilitate their broader adapt practical application, ultimately allowing to more effective communication and control in various domains. And the study presented development of innovative BCI systems that aims to enchain several crucial aspects in brain-computer interaction. First, it seeks to improve cognitive state classification using EEG with great accuracy, allowing for more effective interpretation of user intent. Additionally, the system focused on advanced signal preprocessing method to minimize noise and artifacts, ensuring clear brain signal data, and adaptive algorithms that adjust to individual user variability, enhancing personalization and effectiveness. The BCI system also emphasizes real-time control of external device with minimal latency, uh, facilitates seamless interaction. Lastly, is evaluates performance across various environment conditions to ensure reliability and robustness. Overall, this research aims to create a more effective BCI system for practical application and start about high-level BCI system begins with the brain signal acquisition through EEG, uh, initially utilizing public dataset to develop and test the framework. Once the algorithm were refined using the pre-recorder signal, the focus shifted to real-time signal acquisition. In both cases, signal are processed in the signal processing and analysis model. For data from public dataset, pre-processing is applied to remove noise and artifacts and normalization. And the next step is feature extraction, where relevant features, the brain signals are identified. And the core of the system is cognitive state classification, where the system identifies the user cognitive state in real time and classified state is passed to the application control module, which manages data transmission and configures the microcontroller and ensures system integration for external device control. The entire process ensures that the system can reliability control external device based on real-time brain signals. And something about brain waves. It's different types of brain oscillation known as frequency bands are categorized based on their frequency ranges and they're often associated with specific brain states or cognitive process. And the primary frequency bands include delta, theta, alpha, beta, and gamma. Delta typically observed during deep sleep or in conscious state. Theta are often linked to light sleep, relaxation, creativity, and meditative state. And alpha predominantly present when a person is awake, but in a relaxed state, such as during quiet reflection or closing eyes. Beta it's associated with active thinking, problem solving, and focus. Beta waves are dominant when a person is alert and engaged in cognitive task. And the last, gamma, insolvent in high-level cognitive function, such perception, conscience, and information processing. Each of the frequency bands is linked to different brain states, helping researchers understand cognitive activity and processes based on a gas signal analysis. And we utilized a dataset from the University of California Irvine Machine Learning Repository, which consists of rough EEG recording from a single participant. The dataset includes information about the participant eye state, its open or close, and was collected over a continuous period of 170 seconds using the emotive EEG headset. On the slide, we can see visualization of this data, which clearly shows that EEG signal contain a significant amount of noise. This is common challenge in EEG data, and as artifact from muscle movement, blinking, or environmental factors can introduce substantial noise that need to be processed and filtered out to obtain clear, stable signal for analysis. In the next step, it's analysis EEG data using the Welch method, and the EEG signal is divided into overlapping segments to increase the reliability of the PSD estimation. Each segment in the window using Hamming window to minimize sectoral leaking. This reduced variability in this data and provided more stable estimates of the frequency components. And next step, it's Fourier transform. Its first formula, fast Fourier transform, is applied to each segment to convert the signal from the time domain to the frequency domain. This reveals to the frequencies presents in the signal and helps assess their power. And next step, it's periodogram calculation is calculated for each segment, estimating the signal power across different frequencies, and averaging the periodograms of segments are averaged, producing a smooth estimate of the power spectral density, which reduces the influence of noise. And the step provides reliability estimate of a gas signals frequency characteristic, separating useful information from noise and artifact. This is essential for analyzing brain activity and identifying key frequency bands such as alpha, beta, theta, delta, and gamma. And on the graph, show a sharp spike around 15 Hz. This is interference from electrical device, which can be identified and account for in this analysis. On this slide, display topographic maps for both states, highlighting how the state can affect the gear readings. When the eye moves, the cornea retaining potential is reflected in the EEG, and high amplitude sinusoidal or monographic waves. The study utilizes EEG data collected under two distinct conditions, with the eyes open and with the eyes closed. The conditions significate as they influence the brain electricity activity and can provide insight into different cognitive and neural process. To analyze the data, we create topographic maps of spectral power for each EEG channel in both conditionals. The maps visually represent the distribution of brain activity across different regions, allowing us to observe variation in spectral power between the two tasks. And of course, classification of EEG signal. The system was first tested using a public available EEG dataset. The primary metric used to assess system performance was classification accuracy, and the system achieved a classification accuracy of 94%. It's underscoring the effectiveness of the signal processing pipelines. and specify the Welch method for the future extraction and the Adam classification algorithm and Adam adaptive moment estimation algorithm was chosen due to its efficiency and adaptive learning rate, which makes particularly was suited for complex high-dimensional data like a gas signal. Adam combines the advantage of two other popular optimization methods, ADGRAD and RMS prop, by adapting to the learning rate to each parameters and eventually handing sparse gradient. This anti-fast convergence and more accurate result when dealing with noisy data, which is common characteristic of a gas signal. Its ability for fine-tuned learning process further contributed to the high classification accuracy achieved by our system. In the state diagram, the first row is the state data from the dataset record, eyes open or close. And the second is prediction on the classifier, and third is the smoother prediction, and four in the confidence of the model. And each class in the classification model is associated with a specific command. In this context, users are often required to focus on the cognitive task or external stimulation to elect a brain source. This response is then mapped to the cross-responding class along the BCI system to interrupt and act upon the user intent. And after testing on the dataset, we came to real test for this to choose neural interface on the following characteristic. Its 14-channel EEG provide whole brain sensing for get data collection. Um, of course, it's wireless connective or PC or mobile device via Bluetooth and long battery life. Fast setup, something about motion sensor detect hold head movement, providing additional motion data, and uses that sensor with no sticky gel, ensuring a comfortable experience for the user. On this diagram represents a builder system for cognitive state classification using EEG data interaction with external hardware. Its microcontroller STM32. His description on the floor. The system begins by collecting data from neural interface device. The EEG data is wirelessly transmitted to computer via Bluetooth. Computer processing the received data, performing classification to determine that user cognitive state in this case is open or closed eyes, and based on the classification result, relevant data is sent to the STM32 microcontroller, and microcontroller processes the incoming data, generating an output. In this example, the result of neural processing is represented by an LED, which lights up depending of the cognitive state detect. The system was further validated in real world setting. Get data were collected in real time from two participants performing cognitive task, and the system achieved an average classification accuracy of 88% across participants, demonstrating consistent identification of different cognitive states in the dynamic environment. And this result indicates that system obtain acceptable performance in average accuracy, reinforcing its potential for practical application. And this underscore the effectiveness of the signal processing pipelines, included the Welch method for feature extraction and Adam classification algorithm. The study received approval from the Bioethics Committee of Ternopil Ivan Polya National Technical University. And in the conclusion, the BSI system achieved 88% classification accuracy with 200 millisecond response time, essentially disgusting cognitive states across participant. Welch method was used for spectral estimation, balanced frequency resolution, and variance, which enhanced real-time EG analysis. And the other model, combined with a moving average, achieved 94.55 or 54% accuracy, demonstrating its robustness even with data from individual participants. And the modular architecture allowed the system to scale and adopt to move complex tasks such as controlling prosthetic limbs or smart home device. While the study focused on controlling a simple LED, the result indicates the potential for handling and broader range of cognitive states and more advanced application. This may require more sophisticated classifiers and possibly additional sensor to improve system performance and versatility. And the future work will aim to increase classification accuracy using deep learning, extend the system capabilities to more complex tasks, and incorporate advanced security protocols to protect against cyber threats, especially in critical areas like healthcare or individual or industrial control. Mm, I think I think that's all. Thank you for attention.
Thank you, Danilo. Thank you very much. Very interesting presentation. Thank you. Any questions? Any questions?
Okay, I have one question.
Thank you.
How are you planning to use your research results in future practical development?
Okay, that I say mm, I think it's better for control something device with servo pivot for maybe it's prothesis by its need more medical support. It's not for programming task.
Thank you very much.
Thank you. Any other questions? Okay, thank you very much, Danilo.